I said about earlier how he introduced, well, from Brandon, we introduced the winners. And we also talked about the household chemicals and the application of chemicals in our daily lives. Not to mention, Ryan just included about our environmental practices and also the real life society kind of implications of what we can do with chemicals. Right here, right now, what I'm trying to explain is kind of how to balance the chemical formulas and also show you a little bit more understanding to some specific parts. And that part is being combustion reactions, so oxidative reactions. Oxidative mean reactions that require oxygen, O2. And just as Ryan said something about the rocket fuel, I'll be talking a little bit about rockets. And before that, let's talk about fire. And I know everyone loves fire and it's pretty neat and cool and all, but just like that, fire. So what is fire? Can someone tell me what is fire?
Hot.
Hot. Yeah, it would hot. If I ever touched the puts on my tongue, it would burn. But what? Anything else about fire? What happened? Why did I just twist it? Why did the fire just go up? What does fire need? Where?
Oxygen.
Oxygen. Fuel and what's the last thing?
Heat.
Ignition. Those are that's a very common understanding of fire, right? There's always a fire triangle as you learn it maybe in Alpha Red or in other courses or something like that, or camping, right? You need oxygen, fuel, and heat. And fire cannot start without having these three things. But if you notice something really interesting about this fire triangle is that heat is very big, right? You just need some kind of heat. Fuel can be any kind of fuel. You have tinder, you have wool, you have the wood or the flint of this. But you also need something very specific. And that specificity is what makes fire so interesting. That you need a single element really, and that's oxygen. Okay? So what actually is or composes the physical manifestation of fire? So I'm gonna light our match. And we know why does it give off light? What is actually giving off the light? Well, it's the gases. Hot gases on this fire is heating up at a really fast rate. So what results is that these things are moving really fast and they release light. Light, heat, and all of that. So not necessarily the fuel that gives us the light, it's the hot gases that surround it. The oxygen, the carbon dioxide atmosphere is what gives off the light. Alright? Which is why we can almost compare these matches to, like, for example, the light from our sun. The sun releases a big ball of gas, and that gas is heating up really fast and really hot, and releases light. Similarly, the light here, by producing of the gases of oxidative reactions, form those same gases, and as they heat up, they form light. Alright. So, as I mentioned, what happens when what else is, I only need one more match, is that when we light this match, to prove that this is actually made of gases, what happens when I light this up? When I light, sorry, I don't need another match. Hopefully I have enough matches today. Light this match up? No. And then tilt it upside down. It heads up. Why does it head up? Why will it always head up?
Gases go up.
Exactly. Because hot gases are less dense. So that they will always float up. So even if I tilt this match downwards, the flame still shoots up. And it's all because of that the light is produced from the gases. And because the gases are flowing up, the flame also looks up. Alright, so that's a little general idea of what we know about fire and also about oxidative reactions. Reactions that require oxygen. Remember that fire requires oxygen, and so any kind of explosion or anytime we see fire is a form of the oxidative reaction. And I'm going to write it down right here. So, oxidative reactions require O2, oxygen. Alright? And that's not something that we have seen before. Alright. So let's go back and use that principle onto a rocket fuel. So rocket fuel, Ryan mentioned to us about the rocket fuel engine. It requires a fuel source, right? He said that sometimes we use oxygen in a liquid form, and also we may use hydrogen to gas in a gas form. And it's kind of interesting to note that the oxygen is a liquid form and the hydrogen is a gas form. And this kind of a fuel source and the engine that it uses is called hybrid fuel engine. The reason why we're drawing specific attention to this because oxygen being in its liquid state is much more far easily accessible than it's in its gas form. So I'm going to pose the question to you guys. Why do you think it's better to use liquid form instead of gas form, especially when it comes to using a rocket that we're trying to shoot into space? I'll give you guys a couple minutes. A minute.
What was the question?
And you may talk among each other. That's
Why do we use
The tank has
or versus
finite
gas?
volume.
Well, liquids are way more dense than gases, so you can have more
They don't
for
want it
your
combusted.
Yeah.
amount of
You
space.
also
Oh,
pass the
maybe.
volume.
More danger.
The same with the oxygen. Oxygen requires a lot of,
okay.
it requires like a certain temperature.
Okay, is everyone kind of done? I feel like Ryan has a really strong idea and he's very eager to share.
Yes.
All right, Ryan, share to us. Why do you think we should use liquid oxygen instead of gas oxygen in rocket fuel sources?
Well, because the rocket's tank can only be so big,
Yeah.
and in order to give yourself the maximum amount of fuel,
You would use
Like-
which source?
the one that has a higher density, which is in liquid form.
Liquid form. Exactly. So Ryan just said that we would rather use the liquid form because it's more dense, and because it's more dense, we can compact it into smaller spaces, which could be limited in a rocket ship, correct? And that's a great understanding, but why can't we just compress the gas? Couldn't we just compress the gas too? Wouldn't they somehow end up being the same volume?
Yeah, but that would take a lot of work.
Exactly. That's another idea. So that's kind of a trick question. That yes, we could use the gas, but it'd take a lot more resources, energy, and maybe even like the giant factors required to create these giant high pressure situations. We can easily rather do it into liquid form and just have it incubated into something that's very easily accessible. So that's the reason why we would use the liquid form over the gas form. And to kind of demonstrate kind of a rocket fuel source, I have set up this little tiny demo of the ability of using more dense oxygen to create a higher fuel source. So in other sense, to create more energy using more denser oxygen. So in comparison, I'll take this match, and I've laid up so many of these, and I have hydrogen peroxide here. So its chemical formula is as shown, H2O2. And I propose that it decomposes this into H2O and O2. So it makes it makes oxygen out. However, what's wrong with this kind of question, Ryan? Or actually not Ryan, I'm just another person. Like, what's wrong with this chemical equation?
Is there more oxygen on the right side?
Is the product side, right? The product side has how many molecules or atoms of oxygen? Brandon?
3.
3, right? We have 1 here and 2 here. And how many do we have here? 2. 2. We have 2. So what does this say? What this chemical equation is? Not
Doesn't work?
balanced. It does. Not in a sense it doesn't work. Kind of works, but not in this increment, let's say. So let's say that it still goes in this direction and still forms these products, but not in the set amount. Because the number in front of here, what we don't see, like commonly in math, that we never put an initial 1 here. We never put a 1 here, we never put a 1 here. But there is 1, which means there's 1 molar concentration here will form 1 molar concentration of water and 1 molar concentration of oxygen. And because it's not balanced, this is not true. These set amounts are not equal. So we're gonna talk about how to balance the chemical formula, and we're gonna explain more in detail about it. So let's look at the procedure. So we're gonna write down our reactant side and product side and count each element. So we have our hydrogen element and also what other element do we have? We have
Oxygen.
Oxygen. Right, we want two elements in this case. And we also have the reactant side, R for reactant, E for products. So we just count the sides. How much hydrogens do we have, Brandon?
4.
Here, on the other side.
2.
2. And how many oxygens do we have here? You guys said earlier there were 2. And how much hydrogens are in the product side? Right.
2.
2. And how many are there in the oxygen side?
3.
3. But mainly, it's a good idea to do this as 2 and 1. Sorry, I would probably do this 1, 2. 1 being here and there's 2 here, correct? So to balance this chemical equation, how are we going to get to do that? Well, what's not balanced? The oxygen. So let's try to balance the oxygen first. So this side has more oxygen than this side does. And the kind of trick is to deal with this last standing oxygen last. So instead of having 3 here, maybe I can have, for example, 2 here. Now how much oxygen do I have? Here? 4. Right? 4 hydrogens and 4 oxygen. Whoa. Hey, why did we make more than what we needed? We needed 3, correct? And now we have 4. Well, that's fine, because in the end, what we're going to need to do is balance out the hydrogens. So the hydrogens have 4 here. So how much water molecules do you think we need now? 2. Why 2? Because 2 of it will make 4 hydrogens. And that would give me, it would balance out my hydrogens. And then afterwards, it would balance out my oxygens. So now we look at this equation. Is this equation balanced, Ryan?
Yeah.
Yes. 4 hydrogens and 4 oxygen. 4 hydrogens, 2 oxygens, and 2 oxygens make a 4. So now this whole thing is balanced. So with this chemical equation, we plan to make some water and some oxygen. And let's see we're not true. If we are truly making oxygen, and fire really requires oxygen, then by putting these two together, that more oxygen means I have more of a fire. Okay, that's kind of clear to understand, right? How much time do we have?
8.
So I'm gonna light 1 up, and I want everyone to start counting with me. We're trying, with technology, we can always use a timer, but we're just counting our right loud. We'll be like 1 hippopotamus, 2 hippopotamus, right, guys? 1 hippopotamus, 2
Two
hippopotamus,
rhinoceros,
3
three
hippopotamus,
rhinoceros,
4 hippopotamus, 5 hippopotamus, 6 hippopotamus, 7 hippopotamus, 8 hippopotamus, 9 hippopotamus, 10 hippopotamus, 11,
12 hippopotamuses, 13.
14, 15, 16. So 16 seconds it requires to burn that 1 match, correct? So if I add more oxygen in here, should the match stay up longer or shorter?
Longer.
Longer. Okay, sure. So let's try it. So if I'm gonna put some, this is hydrogen peroxide here. I measured it up for perhaps around 50 milliliters. And I'm gonna pour some yeast. Why am I putting yeast in? Well, it's not really introduced into this course yet, but it's called a catalyst. Catalyst is speeding up the reaction. This reaction right here is a decomposition, right? It's not an oxidative because it's not requiring oxygen, even though it produces it. But this reaction is a decomposition, which means it breaks down. But for something to break down, it might take something time, right? The decomposition rate of a plastic bottle could be like millions of years. To break down this hydrogen peroxide can be a little bit slow, so I'm gonna speed it up with a catalyst. Catalysts speed up reactions. So I'm gonna pour some yeast in here, eyeball it. Very unscientific, but it's okay. And I'm gonna mix it around. Turns kind of mucky and gray and kind of gross. But does anyone see anything about that graph right now? Does anyone see the
Bubbles?
bubbles? So the bubbles is forming up gas. Correct? So let's light up a match. Whoa, did anyone see how it spikes up?
Yeah.
Right? Why is it spiking up? Because it's being fueled by additional oxygen.
No one's counting.
10 1,000, 11 1,000,
But what happened?
15 1,000.
I think the math is still kind of dying already.
Still,
It's kind of dead now. Okay, So was it less than that what we initially proposed of 14 seconds? It actually kind of felt like it was, right? We didn't really have to count, but maybe we should count next time to be more accurate. But it didn't last any longer. But what we did notice was it was bigger. Okay? So just because that you're making more oxygen doesn't mean that the flame is going to last longer. Not necessarily, because it could be resulting on the fuel and the heat. But in the end, when we add more oxygen, we get a bigger flame. And that's what we want to take home from this, is that as you add more, it creates a bigger flame. Alright, cool. So, let me just go over one more example of balancing a chemical equation. And this is really gross. What do you do to it, right? Alright. How much time do I have left?
4.
4 minutes. Okay, well, instead, I'm going to try one more really cool kind of experiment with the orange peel. So this orange peel, the inside is the fruit, correct? It has a lot of water inside. And to protect it, we agree that the peel protects the orange from being eaten by other predators, right? For example, maybe something wants to eat it, they have to peel it first. We would have to peel it first. Otherwise, we'd just be eating a lot of pesticides or, well, this is not as nutritious as fruit, because it can't have much glucose. So in this example of this orange peel, what we have here is that there's a layer of this oil, an oil that protects the water inside this orange, which makes sense, right? So that it would not have any water leak out, because then since oil and water do not like to mix well, then the oil gets trapped on the inside. So using this, I can actually have the chemical inside it is actually called limonene. It's not French, or maybe it is. It's the oil between the orange peel. And we're gonna actually balance it out and make oxidative reactions using some specific rules. So limonene is actually C10H16. Right here, that's the chemical formula for it. And when we make it into an oxidation reaction, so when we expose it to a fire, we're reducing it to oxidation, which means it requires oxygen. And the rule when it comes to oxidative reactions is that, or combustion reactions, is that the molecules that we form are always consistent of what's being burned. For example, carbon here is being burned. So when carbon is burned, being oxidized, it gets broken down to carbon dioxide. And any hydrogen atoms right here gets made into water. So this is the chemical formula. So for example, let's choose another example. For example, C6H12O6, which is glucose. If that's being oxidized, you add oxygen and you form, it has carbon, and then it has hydrogen. We leave the oxygen by itself, so it makes CO2 plus H2O, and all we have to do is to balance it. And this might look familiar to someone, as it is the opposite to photosynthesis. This is what we call cellular respiration. It's something that all living organisms go through. And you're going to have to be able to balance this chemical equation on your own for homework. But today, right now, in the class, we're just going to balance this one up here. Right? So, to balance this, let's repeat our processes. How much elements do we have? We have carbon, hydrogen, and oxygen, correct? And then we have the reactants and the products. All right. Ryan, can you tell me how many carbon is there on the reactant side?
10.
10. Okay. So how much do you think we're going to need on the product side?
We'll probably need 10.
Good. So let's start off that. Break down 10. Because we need 10 of this, and each one of these carbons are decomposed into directly carbon dioxide. So if you have 10 here, we need 10 here. All right, Michael, Your turn. How many hydrogens do we have here on the product side? Reactant side, sorry.
16.
16. Alright. So what number do you think we add on this side?
16.
16. Okay. Alright, how many hydrogens do we have now?
32.
So that's not right, is it? No, it's not. Because this is not balanced. And then what you're going to say is that, okay, there's 16 here, we're going to need to add like 2 of this, right? And you make 2 of that, then you double the carbons, and then you need 20, and it just the cycle keeps on going. So that's not the best option, is that once you make sure that each side is balanced, okay? So, yeah. What instead of 16, what do we need?
8.
Why 8?
8 times 2 is 16.
Where's the 2? Because there's a 2 right here, right? 8 times 2 is 16, so now you have 16. Perfect. Alright, now let's count your oxygen. Because we can always add more oxygen as we get in our demo. Yeah, Brian?
Yes,
How much oxygen do we have on the product side now?
we have,
Can you do some math here? Let's do it.
yeah, we have 28.
28, awesome. So we have 10 times 2 on the carbon dioxide side, and we have 8 times 1 on the water side. 20 plus 8 is 28. Perfect. We have 28 here. And so how much oxygen do we need? Michael now? Yeah, Michael.
14.
14. Perfect. So now we have 28. It's 14 times 2 is 28. So now is this balanced?
Yes.
Yes, exactly. So now we have exactly the same amount of elements on each side. And now that's our balanced chemical equation. So if we burn 1 molecular concentration or 1 mole of this lemonade, then it will require 14 moles of oxygen and will produce that many moles. Okay? All right. So let's just try and do this. Hopefully it works. The experiment requires a little helper, a little bit late. First of all, I need to heat this up because if it's not heated very well, then it will not release a lot of gases for me. Because inside of this orange peel is oil. And you can already see the flame growing, right? Okay, hopefully this is good. Alright, can someone pull the match for me? Brandon.
I'm just staring at you.
Fire.
Work all over again. Okay,
Can you light a match and put it in my hand? Yeah.
That's all.
Oh, yeah, no. Oh no! Oh, I guess it didn't spray as much. Alright, guess we're gonna have to redo this. I'm allowed to, it's supposed to like flame up. Maybe because my orange is really like old.
Have you tried it before?
Got no juice in it.
Yeah, maybe not. Okay, but what we can do is just like, I'll take care of it. Thank you.
What was supposed to happen?
Well, when I spray it, everyone agrees that right now what happens is the flame actually grows, right?
Yeah.
Because it's actually burning the oil off of the orange peel. So when it burns it, it actually creates more of this, and more of this get burned, so it creates more gases, and bigger gases, it creates a larger flame. Okay? So that concludes today's lesson. Make sure you guys take home this question for homework, C6H12O6. And I want you to do a combustion reaction, so add some oxygen to it and then balance it. Remembering that whenever you're combusting hydrocarbon, that the carbon always is made to carbon dioxide and the hydrogen always is made to water. That's it for today. Thank you.